My name is Reiner Zitzmann. I'm the General Manager of the CAN Automation GmbH. It's a 100% daughter company of the association, and the main task of this GmbH, of this company, is to fulfill all the services that are offered by the association to the members of the association. So if you are working together with CAN Automation Association, then typically you get in touch with my person or my team, and we try to assist you to become and stay a vivid member of the CAN Automation Association. Furthermore, I provide CANopen trainings. I represent CAN Automation on fairs, conferences, so I'm a frequent speaker there, and also in the international standardization. You see here listed some projects where I'm active or I have been active. Yeah, briefly to CAN Automation. CAN Automation had been founded in 1992, and CiA is the international users and manufacturers group that develops and supports CANopen and other CAN-based higher layer protocols. The non-profit group has been founded in 1992 to provide CAN-based technical, product, and marketing information. The association fosters the image of the CAN technology and also provides fast future network technologies. We are located in Nuremberg, so in the southern part of Germany, Europe. This is the only office that we have. But from this office, we manage all our activities worldwide. So we are also very willing to come to China and to assist you there in China, your team, your project, So also for next year, I think we will have several activities in China. So I'm looking forward to assisting you there in China, and we are looking forward to assisting the Chinese community. Briefly, with regard to our structure, our development, you see we started in 1992 with 8 members, and in the meantime, we had a constant growth to roughly about 750 member companies directly from mainland China. We have at the moment 28 member companies, but there are much more companies in the region that are using CAN and that are in touch with CAN Automation. So you see here a bit where CAN Automation members come from. Widespreadly over the globe, we find CAN Automation members, and we are from Nuremberg, very keen on assisting you. Anybody who is using CAN, who is faced with challenges in CAN-based networking, then CAN Automation is a good contact, so that you can overcome certain challenges, as we can rely on our social network that we have established since 1992. We can provide you maybe directly with the relevant solutions, or at least we can say, hey, somewhere in our member space, there's somebody located near to you, specified on this solving of these challenges, and then we direct them to you, and so you can overcome these challenges rapidly and finalize your project much easier. So you see, we are very active. And what is CAN Automation doing? So CAN Automation, the center of the CAN Automation activities are the members, the assistance of the members. And one thing that helps CAN Automation members is that you can work based on harmonized data, harmonized services, and therefore the base for that are CAN Automation specifications. That somebody did the work and said, okay, if you want to connect a sensor to the CAN, then the data should be formatted in a certain way, should be provided at the CAN interface in a specific way, so that you give devices in an application field a certain degree of plug-and-play functionality. So therefore, CAN Automation serves as a neutral ground where companies can meet on, and at this neutral ground, they can discuss, can agree on data formats, on strategies, how to exchange data by the means of CAN and CANopen, or maybe J9039 or other CAN-based higher layer protocols. So we are supporting already several ones. And Then we write everything down in a CAN automation specification, and then we release them. Then it's available either for the member space or the member well-proven one, or for political reasons, they are open then for the public and anybody can use them. And around this work with these specifications, CAN automation is offering a lot of services. So some are marketing oriented, some are technical oriented. So the technical oriented services are for educating the people, the engineers, the decision makers, why it is reasonable to use in a certain application field a CAN-based solution. To train the engineers how should a CAN specification or CiA specification be understood and implemented, applied, so we can give you some advice. And finally, we are offering testing services. So we will see later on also for CANopen, we have a test tool, we can do a conformance assessment, or for CANopen FD, we have even the obligation to test the device so that we can call it a CANopen FD device. On the other hand, we are providing some marketing services. So these marketing services allow you, on the one hand, to inform you, to stay informed on the latest updates in the application field of CAN and the latest activities at CiA. So therefore, we have our newsletter, the magazine, we have our product guides, the brochures that tell you why it is reasonable to use a CAN-based solution in a certain application. And on the other hand, you will find there offered by CiA several marketing opportunities where you can inform the public that you are a CAN expert, that you are a user of CAN, you can inform about your latest solutions, or you can place there some commercial advertisement. So this is the service overview of CAN in automation. And for members, we have also the possibility to do some joint marketing. So, for example, establishing some demonstrators at exhibitions to determine where we want to exhibit something, where we want to join our forces to make the CAN visible and to say, hey, also in this application field, it's a good opportunity for communication, a good option. Providing image videos, maybe to overcome language barriers and inform a certain area at the globe why it is reasonable to use a CAN-based solution. Yeah, so you see, we had in the past already a lot of marketing activities, and we are very willing to support also you in China with our marketing activities, our marketing groups, and it's also, of course, for Chinese members possible to overcome some barriers by joint marketing activities supported by CAN automation. In addition, we have also our technical group. There's a strong focus at CAN automation on the work of this development of the technical specifications. You see here our current setup. All our technical activities are steered by the steering committee, the technical committee, chaired by Magnus Hell from company Infineon in the current term. And the technical committee has established several interest groups. They are doing some research, some development to find, for example, the right data link layer for CANxL, the right physical layer options for CANxL. They add some security features to CANxL. They think about timestamping. They think about some issues. How long can network topologies be? How can they look like for CANFD, for CANxL? What about lightweight implementations of CANFD? So all the lower layer activities, so concerning CAN data link layer and physical layer, all this is handled in special interest groups and subgroups of the interest group lower layers. We have then a group IG CANopen that has developed and maintains the famous CANopen protocol. And if there are some things upcoming, then they are in charge of solving all the upcoming issues and informing how can we use the well-known CANopen in current embedded control architectures. Then, derived from the IG CANopen, there's a group that said, oh, we want to use CANopen on a CANFD base. So therefore they say, well, in CANFD, we will see it soon. We have some additional features We have, for example, more data available per data frame. So we want to make use of these improved features of the CAN, and therefore we need to update the CANopen a little bit with regard to the features offered by CAN-FD. And the outcome is then the CANopen FD, which is developed, maintained by the IG CANopen. In addition, we accompany the mapping of J9039 to CAN-FD. This is done in our IG J9039. And as you see here, we have several higher layer protocols now maintained, supported by CAN and automation. And we say it does not make sense to organize the data architecture, the semantic of the data according to the communication protocol. But independent of the communication protocol, the semantic of the data should be identical. And therefore, we say, let's try to describe data that shall be maintained by a certain device class, by a sensor, by a drive, by a controller, in a bus independent way. And then in the second step, we can map the data to the communication technology that we are using, and exactly that we are doing in the IG profiles. So you find here a lot of applications, a lot of device classes, and for them, we're defining the data and the mapping to a corresponding communication technology, maybe CANopen or CANopen. Furthermore, we have a working group for availability, so thinking about redundancy concepts, and we have furthermore the issue safety, security, bootloader that is maintained by these two groups or directly by the task force, by the task force of the technical committee. Yeah, I've already mentioned our publications available for read, write, and advertise, and a lot of things is provided, a lot of valuable information, activities is provided to the public on our website. It's a real treasure case. Some of the information, some of the services are only for CAN Automation members. Therefore, you see here the membership benefits. Yeah, so you should have received now a first insight to CAN Automation. And I don't think that there are some questions with regard to CAN Automation, but if so, you can ask them now. Otherwise, I will continue then with the first talk about CAN-FD and CAN-FD Lite. So for asking questions, you can use the chat function, and or you can now at this moment unmute your micro, ask the question, and then mute your micro again. But at the moment, I don't see any questions, so I will proceed in talking about now CAN-FD and CAN-FD Lite. So just with regard to the language, in my talk, I use the English language. Unfortunately, my Chinese language capability is not that good. Later on, we will hear also talks in the Chinese language. Anyway, I will, where I have some available, use slides with Chinese letters. So it makes it, for me as a referent and a presenter, a little bit more challenging, but maybe for you a little bit easier to understand. Good. Let's continue with the next talk about CAN-FD and CAN-FD Lite. And there, I like to start with a slide here showing us from Bosch and Intel the press release that they are joining their forces in developing semiconductors to a CAN controller, to network devices in a bus line architecture. So they announced that they are implementing the controller area network. It had been in February the 25th in 1986, so more than 30 years ago. And since these days, CAN has made its way in a lot of applications. It's not only used in the automotive section, where it's developed for, with special regard to the use in the cars to network their electronic control units, but it's used in a widespread field of applications. So in construction machineries, in medical applications, in contrast media injectors, patient tables, dentist chairs. It's used by the oil exploiting industry to monitor the conditions around a drilling hole. It's used in ships, in vessels, and submarines. The CAN is used in building automation. So for example, for elevator control, for entrance control, door control. It is so used in solar parks, in windmills. So roughly, or summarizing, we can say the CAN is used anywhere where you can automate something. In some application fields, CAN is the dominating network. In others, it is just used in a niche market, but you find and use the CAN elsewhere. But there's one thing which we can say, you typically have no idea that you are using the CAN, because the CAN is not very visible to the end user. It is typically embedded and deeply embedded in the devices and in the applications. So why is this the case? So the CAN is very robust, is very reliable, very flexible, is available on a lot of microcontrollers from various sources. And therefore, the CAN is very, very interesting for a lot of applications. So it is designed for automotive, so it is applicable for the usage in harsh environments. And therefore, people like the CAN and the simple usage and characters of CAN. But nevertheless, we see the CAN comes somehow to its limits. So we have here an example from Daimler. So it was presented in the times when CAN FD was developed. And there, a guy from Mercedes Daimler has shown how the CAN developed in their cars. So Daimler has very early joined the development of CAN at Bosch. And the first Daimler E-Class that introduced a CAN network was the W124, manufactured from the years 1984 to 1995. And this was the first type of car that integrated one single CAN network with 7 electronic control units, so 7 devices. And these 7 devices were sharing less than 100 messages. So it's not too much information they need to share, and therefore they reduce the cabling effort by employing now the CAN instead of a lot of direct wires. So the next generation, the W210, produced from 1995 to 2002, had already 3 times more CAN networks with about 4 times more devices. So the number of networks increased a lot, the number of devices increased a lot, but the number of messages just doubled. And then there starts the first gap. We see now to the next generation, the 211, the number of networks was not doubled, roughly doubled, let's say. Also, the numbers of SU was less than 2 times of the number of devices of the previous version, but the number of messages was 20 times higher. So it's much more devices that we have now, messages to share, much more information to share. And furthermore, we see here in the next version that we have once again a huge jump in messages to be communicated. And this is a lot of information to be communicated. And the reason is for that more and more software is introduced into the cars. Software is very communication demanding. And due to this reason, we have to introduce more and more messages and to communicate anymore. And therefore, when we have to communicate anymore, we need a higher bus load. And seeing these tendencies that the need for communication is increased, we have to think about how can we increase the bandwidth in CAN-based systems. And these thoughts were made in the years about 2010, 2011 with regard to CAN FD at Bosch. And you see here the requirements. And the requirements that we have here is that you want to have a higher data throughput and a higher payload, in particular to upload the diagnostic memory, in particular to make software updates. But on the other hand, you want to keep a lot of good traditional, well-known features of the classical CAN, that the CAN stays still simple, that you can reuse a lot of knowledge, that you don't have to train the engineers that have used classical CAN today, if they want to step over to CAN FD, that they don't have to learn a complete new bus system, but they can reuse a lot of their already achieved knowledge also in a CAN-FD based system, that you can reuse topologies, that you can reuse maybe even tools. So if you can gain this, this would be very great. And these were the requirements when the car makers went to Bosch, so that you develop the new improved CAN. And we see here the history then, how it goes. So you may know that the CAN that had been presented on occasion of this first press release, for example, was based on the Bosch specification. The Bosch specification 2.0 AB had been the basis for the international standardization, and the CAN is internationally standardized in ISO 11898. And then it was a monolithic approach, and very soon it was seen, well, we want to use CAN in various environments. Therefore, we have to erect, in particular, with regard to the physical layer. So therefore, there was CAN data link layer put in part 1, and the door was open for further physical layer options, a high-speed physical layer in these days, called like that. That what you're familiar with in the classical CAN, running a differential voltage on up to 1 bit rate in a bus line architecture. This you find since 2003 in the ISO 11898-2. There had been also a -3, a fault-tolerant physical layer. And then over the years, there came further international standard parts to this -2, -5 part, for example, that added to the high-speed transceiver also a low power mode, a -6 part that added a so-called partial networking capability, so that you have the ability to put devices in a selective way into a sleep mode to wake them up, while other parts in the network are operating to full extent, and depending on the application state, you can shift the behavior. You can put some devices to sleep and others you can awake. So this had been in the -6 part. And then with the invention of CAN-FD, there came in 2015 then an updated part 1 that is now discussing standardizing not only the classical CAN, that what we had since the beginning, but we have now also the improved CAN, the CAN with flexible data rate, the data link layer in part 1, and a correspondingly improved physical layer in the part 2. And of course, we had to update the conformance tests. So we see here the conformance test from the year 2016, and for the data link layer, and 2018 for the conformance test for the physical layer. So everything had been available since 2018 for using CAN-FD in a tested way. So, and this had been the requirement also for the automotive industry, that everything is well standardized, is tested, so that they can use tested components. So let's see CAN-FD. What was the invention with regards to CAN-FD? The requirement was reuse the classical CAN as much as you can, change only there where it is really necessary. And therefore, it was an analysis by Bosch, and they said, okay, in general, we don't have big issues. We can accelerate the CAN, except of one issue. It is called the in-bit time response in some parts of a CAN data field. So, for example, in the arbitration phase, when you are negotiating, am I allowed to communicate, or is there somebody else out there in the network that is communicating with a higher priority? In this case, I'm communicating, and another one is overriding my bit and informing me, hey, I have a high prior message than you, please stop sending. And to allow this in-bit time response, we have, unfortunately, the trade-off that in this situation, we cannot exceed the bitrate higher than 1 Mbit, because this is the real limiting factor of classical CAN, this in-bit time response. But also we cannot get rid of the in-bit time response, because the in-bit time response is a basic feature for CAN and is the basis for the simplicity of CAN, that you have not to care too much for system integration. You just connect the devices to the network, and the data frames sort into the communication stream based on the priority of the CAN frame. This is possible because of the feature in bit time response, communication within the bit time. And therefore, the guys at Bosch, they thought about it and said, okay, let's think about that way. We keep everything as it is during the arbitration, during the negotiation, who is allowed to communicate. And then, as soon as we have sorted out one station that is now communicating, we are entering a kind of streaming phase. In this streaming phase, there's just one device communicating, no other. So in the streaming phase, if we have no bit time response, then we can turn up the communication speed to what the physical layer is capable. And therefore, we see here in this example, we have used 15 Mbit in the communication, in this data phase, we call it, in this streaming phase. And then when this data transmission mainly is over, then you have once again an in-bit time response during the acknowledgement. During the acknowledgement, somebody tells you, hey, I have understood your message correctly. And therefore, we have here another CAN feature that introduces in-bit time response. We want to communicate it. And therefore, we have to respect the same communication limits as we had during the arbitration phase. So we see at the beginning and at the end of the CAN frame, we have strong restrictions with regard to the bitrate, but in the middle, we can turn up the communication speed to what the physical layer is capable to drive. So you see here an example based on classical CAN transceivers. We turned up the communication speed in the data phase to up to 15 Mbit. In this example, don't take them too serious. Just as a reminder, in the international standards, you will find 2 Mbit or 5 Mbit for the communication speed. These are some realistic values, also considering some topology issues or having some topology issues in mind. But in general, when you just think what is really possible, then you see, okay, the limiting factor is then my topology and others, but CAN FD would allow increasing the speed dramatically. So you see here the screenshots from the oscillator. We start with a CAN frame, and I think you're familiar with a classical CAN frame. You have the arbitration, mainly that part where you find and code the CAN identifier, and then somewhere you switch over in the data data frame to an accelerated bitrate. That is, of course, pre-negotiated and pre-configured in all the devices. They have to know to which bitrate we are jumping. In this case, these 15 Mbit, and then you communicate here your data with a much higher speed, much more data, and then you switch back to the speed that you have used at the beginning at the arbitration phase. You give the acknowledgement, and then you end the communication. So this is the basic concept of CAN FD. And to increase the efficiency, there was then the idea to also increase the length of the data field. Not to stay with just 8 bytes, but to use a longer lengthened data field with up to 64 bytes. So we see here, what can I gain with CAN FD? With CAN FD, I can gain, for example, here when I turn up just the speed, that what we see here on this chart, So it is derived from Florian Hartwig, one of the developers of CANFD, and he presented it on occasion of the 13th International CAN Conference in 2012. So this you find also the white paper, and I think also the speech you find at CANautomation's website or at our YouTube channel. So you see here, when we start at 500 kilobit and we turn up the communication speed in the data phase, what can we gain? And if we turn up, for example, the data phase communication speed to 4 Mbit, then we see, okay, we end up at an average speed of 1.4 Mbit roughly. What does this mean? Practically spoken, I could say, okay, I can use an existing protocol stack. So for example, a CANopen stack that had been designed for classical CAN, that is just capable to run 8 bytes of data within a CAN frame. And I can put this on a CANFD controller. And using that, maybe in this setup, I would already get increased data throughput because I transfer the data no longer in classical CAN, but in CANFD messages. And in that way, using this bitrate setup, I can increase the data throughput in my system. And I have no change more or less in the protocol stack that I'm using. This is just one information that we can derive from this slide. If I want to make full use of CANFD, then we see here, of course, we need a stack that is adapted to the data length of a CANFD frame that is capable to run 64 bytes of data. This is the maximum length of a CANFD frame. And we see here, if we start with the setup that we have on the previous slide, that we transmit 500 kilobit in the arbitration phase and 4 Mbit in the data phase, and that we increase now the data field starting at 8 bytes up to 64 bytes. So in other words, that we increase the amount of accelerated bits. Then we see here the average speed of my network is increased up to roughly 3 Mbit. So you get a first idea, what can I gain with CANFD and which kind of data throughput jump can I achieve by means of CANFD. So summing this up, we come also to some system design features. So CAN with flexible data rate, where when you ask, what can I achieve with CANFD? It's not that simple to answer because it depends on some features where you have first of all to think about what you like to achieve in your application by the usage of CAN. Is it just using a lengthened data field? Is it a higher communication speed? Or is it both together? And depending on your needs, you have to think about how you apply, how you use CANFD. So when CANFD came up, we asked our member space for which purpose you need CANFD. And the astonishing answer was, we are not keen on a higher communication speed. What we need is lengthened frame. We have some troubles with the 8 byte border. We need a 12, 13 byte. And this byte we want to fill with some additional information because we have not only to communicate the pure sensor value, but also the status of the sensor, also some diagnostic data, some surrounding information, under which condition was the sensor value taken. And if you have such a requirement, then these 4 byte or these 8 byte of data get a little bit limiting that are provided by the classical CAN. So if you say, okay, I have not big timing issues, and therefore I can just use the CANFD frame without a jump in the data in the data rate, then all the communication rules with regard to the physical layer that apply to classical CAN apply to CANFD as well. What does this mean? I can totally reuse today's classical CAN physical layer implementation. I have to change nothing. And this can be a great benefit in a lot of applications for transiting from classical CAN to CAN FD. And furthermore, in some applications, it may happen that if you are running CAN FD frames carrying 64 bytes of data with just a classical communication speed, that this may place too much latency on your network. So to avoid too high latencies, you can say, okay, I do just a little jump. Maybe today I'm communicating with 125K, and then in future I use CAN FD and I just jump to 500 kilobit in the data phase. So this small jump assures that the latency is kept low in your application. And on the other hand, the impact on the physical layer design of your network is very low. The impact on your physical layer design gets always large if you increase the 1 Mbit. And if you're doing so, then you have to evaluate very, very carefully under which circumstances this CAN FD network will run. Because then you get some, or you have to work very precisely. All the well-known liberal rules of classical CAN are disappearing then. So in classical CAN, you typically have, I call it a kind of gray zone where you can make a lot of mistakes in network design, and nevertheless, the CAN network will work, will operate, maybe not in the best shape. You will see maybe some error frames, but at the end of the day, it will work. In CAN FD, using a high communication speed, a high jump in the bitrate, this may cause that this band for tolerance, for allowing errors, this will get much smaller and you have to work much more precisely. And therefore, you should evaluate very closely, okay, which bitrate jump do we need and which do I want, and what are the consequences then for my physical layer design. Yeah, so much with regard to CAN FD. You see here, in principle, the file format, the frame format in comparison, classical CAN to CAN FD. They are looking quite similar. They just differ in some bit sizes. So, for example, we see here we have 3 additional control fields. I just give you a hint for one secret. So, 1 bit is used to indicate are we in the classical CAN frame or the CAN FD frame format, 1 for bitrate switching, and further bits are used for indicating the size of the data field. We have now an enlarged data field. We can carry up to 64 bytes of data. And of course, depending on the size of the CAN frame that we want to ensure, to secure, we need a corresponding CSC that provides the corresponding quality and gives us the security that we work with correct data only. Yeah, some details on the CAN FD frame we receive then later on in the later talk. Therefore, I do not talk about the details of CAN FD here in my talk. I just want to give you an idea with regard to CAN FD and the implementations of CAN FD. So don't worry, all the new CAN controllers that can CAN FD use also or can also understand and work with classical CAN. So you have 3 implementation options according to the ISO. It's classical CAN only, it's classical CAN and CAN FD, and CAN FD tolerant. So these are the implementation options according to the ISO, and you see here in this slide the compatibilities. So if you want to talk classical CAN, it does not matter which kind of CAN implementation you have, either classical CAN, CAN FD tolerant, or CAN FD, all can talk with each other with classical CAN frames. As soon as you want to use CAN FD, it gets more critical, and a real CAN FD based communication is only possible if all the devices support the CAN FD. So Availability is no issue anymore. So you get CAN FD controllers almost from all the semiconductor manufacturers. So you can browse, for example, for the CAN newsletter, one of our implementations, for having an idea about the availability. Stacks that are directly designed for CAN FD, like CANopen FD. There are some manufacturers as well. The protocol manufacturers depend on a certain application field. So you can contact them and they can provide you also with adapted software for the higher layer product. Just some for finalization, some reminders with regard to the physical layer. The physical layer had been updated in context of the introduction of CAN FD in the ISO 11898-2 from the year 2016. And it's not just giving you the idea how to set up a CAN FD physical layer, but it gives you the data, now the operating limits, also for the communication speed of 5 Mbit, 2 Mbit, and also merges the low power mode and the partial networking that had been introduced by some other parts, -5 and -6. So you have now one monolithic specification. The physical layer, all the learnings that we got while writing the standard, we tried to save in the series 601. So physical interface implementation, controller interface recommendation, system design recommendation. So please browse out the CANautomation's website and find there the physical layer recommendations that we say. When we had recently an event from CANautomation organized, there was someone from Kongsberg. They're making for these huge vessels the control networks, and they said, we want to use CAN FD in our applications, but for us, some networks running in the size of an engine are not very interesting. We want to use CAN at 250 meters, 500 meters. And how does this work? And therefore, CANautomation founded a group, the large CAN FD, CAN XL topologies. And they want to see how can you set up large CAN FD networks. And we did some first assessments in this group where you could run CAN FD at 500 kilobit or 250 kilobit in the arbitration phase, and about 2 Mbit in the data phase at a length of 200, 250 meters. Frequency dependent damping was somehow a limiting factor to not getting larger networks than that, but it looks good that we can achieve something about 200, 250 meters of network length for CAN FD in such a setup. For CAN XL, we had recently in Detroit a Plugfest where we did some further assessments. So you see here a link to the CAN newsletter from June, where you get some further information, which communication speeds we achieved in which setups. So this is, of course, not limits. This is just a showcase that you see, okay, also with CAN XL, we can get hybrid architectures, and we are not that strictly limited to a limit. We can have stub lines, we can have stars, and so on. So if you want to join the group, then we are we appreciate very much your support. And finally, I want to give you some information on CAN FD Lite. So it is not increasing the power of CAN FD, but is reducing. And what is the key driver? The motivation for this is that the automotive industry is shifting from the domain-oriented architecture to a zone-oriented architecture. A zone-oriented architecture is introduced, on the one hand, to introduce the wiring effort. On the other hand, it is somehow similar to the way you communicate in cloud applications. All the data has to describe themselves. So you need a lot of payload to describe a single data point. And in these zonal architectures, you have also the condition that in best case, one central controller has to control a lot of MCUs and you want to save your resources and to want to keep these devices that you connect here very, very simple. So in the best case, you move a lot of functionality in the central controller and have here very, very simple devices. And this approach is now this CAN FD Lite. And the CAN FD Lite sets up a communication that follows a commander-responder schema in broadcast. There's one commander that controls the communication. And for example, in a light application where you have a lot of LEDs now controlling the rear light of a car, for example, and making there some patterns. And these light controllers, they are just simple responders, just reacting on the commands of the commander. Therefore, the light actuators can be very small, very lightweight implementations that can control the light sources. CAN FD with a frame length provides a lot of data throughput that allows the control of a lot of LEDs, far enough for controlling today's cars. And we can use already existing bus technology, the CAN FD transceivers, and we can, as we have just a commander-responder communication, we can use implementations where several, let's say, light units, light actuators, share via one transceiver the bus access. So several responders on the same printed circuit board connected via one transceiver to the bus, because we have some restrictions in CAN FD Lite. So what makes CAN FD Lite? So it's a lightweight implementation of CAN FD. It's just a subset. Responders are synchronized to the commander. So we don't need any frequency setting external component. No crystal oscillators are needed in the responders. So we have no responder to responder communication. Therefore, we don't need an arbitration. We have no error frames, erroneous frames. They are just ignored. And we have also no ACBIT detection. So there's no acknowledgement. So a lot of simplifications we do in the CAN FD Lite responders to allow very, very simple applications and very, very lightweight implementations for these kind of applications here. So I think this can be very interesting for diagnostic purposes. We are introduced here a simple addressing feature that allows just in unicast a communication. We have the addressing, and you can ask for certain data points, and then with a certain delay, the responder gives you the information. Yeah, just summarizing, lightweight implementation of CAN FD is the CAN FD Lite, and it is now introduced and added to the ISO that is introducing CAN XL, where we hear at the end of this technology something about, and some further documents like the recommendation, the system design recommendations and requirements. This is in progress, and the same is also the conformance test plan. Yeah, so much with regard to CAN FD and CAN FD Lite. Are there any questions? So as I've already said, for questions, you can use the chat function either, or you can unmute and you can use directly the audio function. Okay, at the moment, I don't see any questions. And therefore, as we are a little delayed, I say I would continue now with CANopen FD. You see Mr. Chen is then subsequently informing us about some details to CAN and CAN FD. Okay, so CANopen FD, let's talk about CANopen FD and why do we use it, why do we need it. So I have very briefly introduced CAN FD, and I have shown to you that CAN FD is now based, or is now coming with lengthened data frames. You have now the possibility to communicate within CANFD 64 bytes of data within one single frame. So, of course, I can put on a CANFD frame now a stack that is just capable to operate with data messages, data frames that have a size from 0 to 8 data bytes. This is possible. I have no need to use a 9th, 10th, 11th byte. So this means I can use CANopen based on CANFD, and I'm fine. I can have even some benefits. I've showed in some slides before that I can increase the data throughput in a CANopen system by using CAN. But if I want to use the full power of CANFD, I need to have some software that is capable to run larger data bytes that may carry up to 64 bytes of data. So, and this was now the key driver for the development of CANopen FD, that we said, let's update our existing communication objects in CANopen with regard to the usage of CANFD. And when we are doing so, we can analyze which communication objects in CANopen are limited by CAN frames, need some adaptations. Where can we, is it maybe better to stay with the already well-known functionality, to make not just a new protocol, but to keep all the good, well-loved attributes of CANopen, and to do just only at those points some changes where I have really a significant benefit of CANFD usage. So this was the motivation, and the outcome was then the CANopen FD. So as I've said, we want now to make use of CANopen FD, and therefore of 64 bytes of data. Not necessarily always 64 bytes. We want to do it use case dependent. Maybe sometimes 56 bytes of data are sufficient, and another time 3 bytes of data, but we want to have the ability to use 64 bytes of data, and we want to have the ability to communicate in an accelerated speed. So when we were defining CANopen FD, then there were a lot of people around the table, but most of them were protocol stack manufacturers or providers of some devices with CANopen, but they weren't CANFD physical layer experts. So they said, well, that's no problem. We have already CANFD physical layer experts in CAN automation. They have written these documents I've shown in one of the last slides of the previous talk. And we just refer to these documents. We don't have to be more wise than these guys who are experts in CANFD. So we just reference to these documents and say, a CANopen FD physical layer has to fulfill the rules and the recommendations as given by ISO and the CiA 601 series. In addition to that, it was clear, well, we have to define the bit timing. And if you analyze a little bit deeper and more closely the physical layer specifications for CANFD, then you see CANFD with bitrate switching works then very well if all the devices derive the bitrate from the same oscillator frequency, use the same bit timing register settings, and operate based on the same time quantum. And then we said, okay, these are nice informations, but we don't want to bother the end user with something like that. There we want to just say, okay, give us some pair of bit rates and don't talk about bit timing settings and whatever. So in CANopen FD, we defined some bit rate settings. Here we see these pairs of bit rates should be mandatory for all the devices based on an 80 megahertz frequency clock. And the specification itself has, of course, the bit timing tables that should be adjusted in the microcontroller and the CAN controller. But the end user can just say, okay, I use the first, second, or third pair of bit rates, and all the CANopen FD devices should support them. Then it got clear over the years, well, for very small sensors, it's better to use very small microcontrollers that maybe just support 40 megahertz clocking, and then you running at 5 Mbit in a data phase, it gets tricky by the adjustment in the bit time registers. Therefore, this in the next CANopen FD version is no longer mandatory. You see it here. These are the bit timing tables based on 40 megahertz clock. In the next version of 1301, the CANopen FD specification, where you see, okay, these are the bit rates that are mandatory for the arbitration phase, and those are for the data phase. And therefore, I can say, okay, I have all the bit timing settings, I have the data rates, and I can just make a simple rotary switch and set on a certain setting depending on the table index, and I'm compatible to other implementations following this table. So in CANFD, the physical layer may be a little bit challenging. You have to work much more precisely. As a good base, I think we have this table now in CANopen. In principle, in CANopen FD, we want to continue with all the good things that we have already in CANopen. And this is, of course, the device model, the device architecture. You see here the CANopen device model for CANopen FD, and it's identical for classical CANopen. Classical CANopen and CANopen FD are rather identical. You don't find such a description in a classic CANopen specification, but implicitly it's there. When CANopen had been written, we were not using UML diagrams. Now in CANopen FD, we have something, such a feature, so we can do it. And you see here it, CANopen device resides on a CANFD device, and they reside on a field device. The CANopen device inherits the data rate and the bitrate settings from the CANFD device, introduces a node ID, and here we have something new. A CANopen FD device has now also a network ID. So a CANopen FD device may have the knowledge, what is my network where I'm in, and what is my node ID. So I have now an additional identification number. In particular, if I operate in cloud-based applications, in IoT applications, it is very important to know where resides the device, in which network resides the device, so I can get all this information then to my data and all this information then for some web-based application for whatever purposes. But all the rest is identical and just more precisely depicted here in such class model. The communication states are completely identical. We just describe them a little bit more precisely, but this is as they have been ever intended in classic CANopen. We have this now also in CANopen FD. We start our device, we set our network ID and node ID. Then as soon as we have everything set, the device initialized, we enter communicating with the states pre-operational, operational, and stopped. In addition to that, we take care also about the manager, or maybe formerly known as master functionality. When does this kind of functionality start? Also, this is clarified in CANopen. And then, as I've said, we analyze for all the existing communication services, which service can really benefit in a significant way by the fact that we carry now the service via CANFD, or is there no significant gain? And if not, then it is maybe more beneficial to keep the service as it is. We analyzed this and we thought, okay, there are several services that are not limited by CAN. They stay as they are. And all the data services that are somehow dealing with data transport, process data, service data, diagnostic data, they are limited by classical CAN frames, and therefore they need an update. The process data object, service data object, and the emergency protocol. Let's have a brief look. We see here the way the CANopen PDO works. So PDOs carry process data up to 64 bytes, and CANopen devices recognize a PDO according to the unique CAN identifier. The unique CAN identifier is coded in the PDO communication parameters. So for example, here, my CANopen device sees, oh, there's a CAN frame incoming with a CAN identifier 181. And then the CANopen device says, oh, this CAN identifier is familiar to me because it is configured here in the communication parameters of my received PDO1. The corresponding mapping table is here in the corresponding mapping parameter 1600. I have 3 objects mapped, and I have also the size of the data. Also, this information is provided in the mapping table to this PDO. And I can go like that. I say, okay, take the first 8 bits of this received data, store them to 2000 subindex 1 in my local object dictionary. I do so. And I see, okay, this 21, this is a temperature value in degrees Celsius. Let's take the next 16 bit, and let's store them to 2003 subindex 3. So I take these 16 bit, store them to this index and subindex, and see, oh, there's a depth value in millimeter. And take now the last byte, the last 8 bit, and store them to 2003 subindex 1. Oh, this is an height value. So this is the way the PDO works. And there's no limitation. I can do this for 8 byte, but in the same way I can do this for 64 byte. So no change was necessary. We have the same mapping table. The only thing that we had to change was the threshold value from 8 byte in CANopen, because classic CANopen messages have just 8 byte, to 64 byte, so that I can use a CAN frame. For the SDO, that's a little bit more tricky. In the SDO, we have the position that SDOs are defined like that. That typically the server determines the CAN identifier of the CAN messages that are used in this communication for the diagnostic communication or the configuration communication that I can access maybe from a host controller, a sensor, a motor, to configure how fast shall the motor rotate, what's the current status of the motor. So this kind of communication is typically determined by the server. We know this as the first SDO server channel. So node ID of this device plus this offset results in the first default channel that offers the access to any CANopen device. And if I want to have a cross communication between devices, this is possible in CANopen, but I need always identifiers. I need someone who configures here and there the pair of identifier to allow a fully cross communication. So CANopen has already the availability to describe and to set up an entire meshed CANopen network where every CANopen device has SDO communication channels to all the other devices. But it is combined with a huge configuration effort if you want to do so, and you waste a lot of CAN identifiers. This is a limited resource in CANopen, and you need a lot of identifiers, as for every communication, you need 2 identifiers so that every device can access every other device. So CANopen has this, but typically the implementations are limiting. They don't allow a second or third server or client implementation. So in theory, we have this functionality. In theory, we have also the functionality that we can establish dynamically during system operation, cross communication between the devices. But then we would need a functionality, a controller that is able to establish these dynamic channels. We have specified this, but unfortunately in the market, it's very rarely seen in the application. So I cannot rely that a CANopen system has an SDO manager function. And also the communication over network borders, exceeding network borders, there we have something for SDO. But always we need someone who configures. So CANopen comes from times where processing power at the microcontrollers is a limited resource. Now we have much more processing power, and therefore the fathers now of CANopen FD said, why not get rid of the limitations of an SDO and introducing a new service that can overcome all these limitations, that has the full function coverage of the classical SDO, but adds some additional functions. So where I can have, on the one hand, the access to all object dictionary entries of all the devices, where I can carry all the data in independent which size it is, in case of doubt in a segmented way, but where I can have not only unicast communication, but also multicast or broadcast communication, where I can have parallel communication between the devices, where I can access dynamically during system runtime, this device or that device, where I can establish dynamically during system runtime SDO cross communication by absence of a manager functionality. So all this has been introduced in CANopen FD now in the SDO. So we see here briefly the USDO has been designed in a way that we have took care on byte alignment so that it's easy to implement. So we have fixed CAN identifiers determined by the sender of such a CAN frame. This means we do not rely anymore on limited CAN identifiers. And the trick was now we determine the destination of this frame in the first byte of this CAN FD frame. So you can filter also on this first byte in modern CAN controllers, so no big deal on that. And this gives you the freedom to say, okay, now I want to speak to device number 1. Oh, later on, I think I want to talk to device number 2. So it's very easy for a single device to establish cross communication to any other device that is in the network. So you can have also group management. This means you have multicast communication or broadcast communication. I want to talk to all. So this is very advantageous, for example, for seating machines where you have 100 motors and all have to configure in the same way. It's just one command. We will have later on an example for that. You have here several types of the SDO communication as we had in the past, segmented, accelerated for large and small data packages. You can have several transactions at the same time to one or several different devices. And then the addressing, of course, with index, subindex, data type, size description, and then have the data and the payload of the CAN frame that is used is adapted to the really required one. So we are not carrying always 64 byte frame, but we adapt the payload of the data link layer frame to the really needed payload. So we have also the segmented transfer. We see it here. And we have also a bulk transfer. So where we see, okay, we have just a small prologue where we negotiate, okay, how we want to communicate, what are timing issues. So we have here the possibility to communicate timing restrictions. And then when this is done and accepted, then I can send one message after the other. And I can accelerate dramatically by that, for example, a software update. Yeah, the USDO has already the inherent capability to communicate via network borders. So I have here the capability also to say, please direct this answer to this network and there to this node. Of course, I need some knowledge on the network architecture, on the entire system, but as soon as I have it, I can communicate like that. And you see here some examples. So this USDO eases dramatically end-of-line production, several devices of the same type, one SDO access, which is needed here to download the same software to all these drives. In the meantime, while I have several transactions, I can double check, is everything okay? Now, what is the current status of uploading the data? I said already the example seeding machines. Several drives need to be configured identically. One USDO access instead of, for example, here, 20 single SDO accesses. So dramatical reduction of time. And also here maybe, in particular in China, I know you have a lot of these light electric vehicles, and sometimes the end user does some configurations here, adds devices, gimmicks, batteries, whatever. And if the end user changes, modifies the system setup, it's very good if you have such a feature like the USDO, which can dynamically establish cross communication channels between the devices, can get familiar with devices, can double check which functionality has been introduced into the system, and can work with this functionality. So this is a very big jump in functionality in CANopen networks, what has been introduced now by CANopen FD USDO, and also very valuable for USDO for IoT applications, where you can say, okay, on demand, I can access any data point in my application. Good. Due to lack of time, just a small information with regard to emergencies. The emergency state machine was kept identical to CANopen, but the emergency message communicating an incident, this was adapted. We have here the classical part from byte 4 to byte 11. This is identical to the classic emergency message. Due to byte alignment and some other reasons, we have prior to this and later on some additional information. So we can now identify which logical device had this issue. So we have now more and more complex devices where several device functionalities are encapsulated in own logical devices on the same printed circuit board. So it's better now to fine-tune where's the source of the error. We can have time stamping, we can have more detailed error information, and we can also have a detailed error history, a very deep error history, and then we can analyze what had been the reasons for these error cases. Yeah, so I have some listing of new functionalities that are available, new data objects. This you can browse by yourself, I think. This is not just paperwork, it had been tested in several Plugfests. The specification is released. We are now going to release a version 1.1. It's just in the pipeline, so I expect the new specification in the next days. And one thing I like to remind you with regard to CANopen FD, if you want to call a device a CANopen FD device, then you have the obligation for testing. At the moment, we don't have a test tool yet. We have a small checklist, which we are checking that allows to give you a minimum for performance assessment and a good feeling, okay, the basics of CANopen FD are really implemented. You have also some first implementations available of CANopen FD stacks, first IO devices, first host controller exists also for microcontrol. Company EMSA offers CANopen FD gateway. So we see everything is available for starting with CANopen FD. And if you're interested in that and you want to join the group, to join the activities, you want to submit some requirements, then please feel free to do so. Any contribution is appreciated.